The engineering design process consists of 4 given stages: conceptual design, preliminary design, detailed design, evaluation and acceptance. If, after the final step, the requirements aren't met, the whole process starts anew. Otherwise, the product is accepted. In this video, we'll be presenting how we apply these 4 stages to a wing design. During the first stage, the conceptual design stage, we discussed how we want to tackle the problem. Which structure do we want to choose? What are our requirements and how do we meet them? How do we make manufacturing as simple as possible while also keeping the mass low? And finally, which spar cross-section we want to go for. During the second stage, the preliminary design stage, we tried analyzing documents provided to deepen our understanding of how our wing would behave in different situations and how we could improve its overall performance. In the beginning, we relied heavily on the Excel spreadsheet and its predicted outcomes. Although it proved very helpful when trying to find spars that would fit into the rib section, we soon found out it was very flawed, so we used it more as an introduction rather than a guide. We found SolidWorks much more appropriate, and since then we used it to gather data from multiple spar simulations, while trying to find the best mass to performance ratio. Thanks to the data gathered, we found parts that are crucial to wing structure, and we used that information for the next stage. For the third stage, the detailed design stage, we use computer-aided design to help showcase a wing. It also helped us to visualize how we would assemble all the parts. During this stage, we were trying to find the best design that would also be the easiest to manufacture. Using SolidWorks, we created the final model for a wing, which included trailing edge, leading edge, the ribs, and the spar. When it came to manufacturing, one must always remember that due to human errors and imperfections, the final product will always differ from the initially designed one. We, as engineers, need to work with exemplary precaution to minimize those errors by, for example, taking multiple measurements. Both Excel and SolidWorks predictions turned out to be imperfect, so we had to produce several spars and test them individually. In the end, we went for the presented design. 40 by 40 part is 41 cm in length, the 30 by 30 part is 30 cm in length total, with a 10 cm shoulder inside the bigger part. In the beginning, we also wanted to go for 10 mm thickness ribs, but in the end we gave up on that idea because we wanted to save mass. For the fourth stage, the evaluation stage, the end product is tested in several ways to evaluate its performance. We had to test how much our wing could withstand in terms of both torsion and bending moment. For the torsion test, for a given force arm and weight, the twist angle can be easily calculated using trigonometry. For the bending moment test, we kept on increasing the point load and recording the deflection of the spar until the wing failed under the load. We also made a mass breakdown that is currently being shown. Then we compared all of our predictions with the actual wing data. Our wing failed when a load of 1.1 kg was used, making it pass our requirement of withstanding 1 kg. Our initial spar was very light but incredibly fragile, so we had to abandon our first design. It's incredibly important to understand why the shown data differs so much. The discrepancies are caused by such means as inaccurate material properties, approximation of the chosen theory, and imprecision in manufacturing. Worth mentioning is also the fact that in real life wing design is a much more advanced topic because of uneven weight distributions, differences in pressure, or even the addition of fuel tanks or engines.